two forces P and Q. They're acting on a block that's placed on the table. Okay, so just to I don't know if I'll be able to do this with my trackpad, but I'll try here. Let's comment. Let me comment. Okay. I'll try and see which class period it was we covered unit vector notation, but just to kind of refresh our memory here, in 3 dimension, like if this was the positive y-axis and this was a positive x-axis. Sorry, it's gonna be even worse than my usual handwriting because I'm using the trackpad. And this is the positive. Oh. Let's see. Then I is a unit vector that points along the x-axis. J hat is a unit vector that points along the y-axis, and z hat is a unit vector that points along the k-axis. K hat is a unit vector that points along the z-axis. And unit vectors are vectors that have a magnitude 1 and they have no dimensions. And so that's why that word unit, because they have a magnitude of 1 and they don't have, so whatever you multiply them by, they take on the dimensions of whatever you multiply them by. So in this case, we're multiplying by this scalar force, and now they take on the dimensions of a force. And then the unit vector is what gives it that direction. So in this case, like P has an x component, because I hat is along the x direction. It has an x component that's 1.1 newtons in the minus x direction, and a z component that's 4.25 newtons in the z direction. Does that make sense?
Yes, that does. I understand that part of the unit vector. However, how do I solve a problem like this?
Okay, so the magnitude and direction of Q are unknown, and that is unknown, and that's one of the forces that's acting on it. Where there's no friction, the mass of the object is that. So when it's moving at a constant velocity, what does that mean for the net force?
There's no acceleration.
Yeah, so there's no acceleration, so the sum of the forces is 0, right?
Mm-hmm. So it'd have to be opposite signs for both things, or for both values.
Right. So that means that that Q has to be plus 110 I hat and minus 4.2 K hat. And so that's, so when we go to put it in here in WebAssign, then what it wants you to do is use the unit vector notation. And maybe that's where it's telling you that it's wrong, is because it wants you to put in the unit vector notation.
That part A I did figure out, but I started struggling with part B. Like, how do I solve that part?
Okay, so now it's telling you that the sum of the forces is no longer 0. Now it's got some acceleration, but we know what the acceleration is. And so the thing to remember with this is that we're going to apply Newton's second law in each direction. And so that's really the big thing to remember, is that this force has an x component and a z component, and this force Q has an x component and a z component, and those two forces add up to produce an acceleration that also has an x component and a z component. And so we're going to break it down into each direction. So we're gonna write down Newton's second law in each direction. And so let me see if I can do that on the PDF file, and then why do I have 1,000 PDFs? Here we go. That's not. What? No. Let's go over to the tab. There we go. Let me just do the text box here. So like if we do, I'm just gonna write it in words because but normally we'd put the sigma there, right? We do sum of the comment. Sum of the forces in the x direction. I do not advise trying to write stuff with the trackpad. Maybe some of y'all are great at it, but I cannot do it. That is not. And the trackpad just quit working. That's awesome. All right, so if we take a look here, what forces do we have acting in the x direction?
So we just have, we have the acceleration force. So that would be negative 5.5. So that would be.
Okay.
And
yeah, I'm sorry, go ahead.
The mass as well would also act in the x direction. But how would P also be factored in? I don't know how that worked. Would it be added to Q? Or I'm not sure there. No, it would be.
Yeah. So it is. So it works just like if we had written these forces individually. So that's what we're gonna do, is we're gonna take each component and write down a separate Newton's second law for each component. So in the x direction, we have the x component of that force P, and I'm not going to be able to put the vector hats on them, so you'll just have to imagine that they have their vector hats. And the x component of that force Q. Does that make sense?
Even though Q is just the acceleration.
Q is not the acceleration. So Q is our unknown force. And so then the acceleration appears on the other side of Newton's second law, because these two forces add up to produce the x component of the acceleration. This should really be a subscript. But
okay.
Yeah, it's kind of, I can't make it, for some reason I can't make it a subscript. Yeah, just X as a subscript. I can't, for some reason I can't figure out how to do a subscript. So along the X direction, then we've got the X component of P, the X component of Q, which we don't know, and the X component of this acceleration. And then we know what the mass of the block is. So sum of the forces produces an acceleration. So like if we do that again, we'd have like that equals minus 1.10 newtons plus we don't know qx, excuse me, equals 4.65 kilograms. And then the x component of the acceleration is minus 5.50 meters per second squared. And now, if we solve that, that'll get us the x component of q. Does that make sense?
Yes, that makes sense now. And then the z would, or the k hat or z direction would be attacked in the same way.
Yeah, that's right. So then we find the z component exactly the same way, which is using the k hat component. Yeah. So we do some of the forces in the z direction, and then I'm just gonna. Ooh. I'm just gonna write sigma there. So we have PZ plus QZ equals MA, and then that's the Z component of the acceleration.
Okay.
And then and so then it works the same way. We got 4.25 newtons plus QZ equals then the whatever the Z. I'm sorry. Yeah, whatever the Z component is, 2.25.
Okay, that makes a lot more sense.
So then how would you do the next one, you think?
I would use the same concept of it that was in part A, which is every force has an equal and opposite reaction. Since it's the same acceleration, just the signs are flipped. I would assume it's the same force, just opposite signs. If that makes sense.
Oh, I get where you're. So, I think you have to be a little bit careful about that. It's a good thought, but I think really what you want to do is just go through this again.
Okay.
It might be. I don't know if that's necessarily the case here.
Don't you just change the sign of the accelerations when you plug it in? And everything else is basically the same?
Yeah, you're going to change the signs of the acceleration.
Okay, that makes sense.
So you're basically just doing the summation of the forces in each of the directions that you have something for in the unit vectors, right?
Yes. Yeah. So again, so writing down these forces in unit vector notation is a different way. Is a different but equivalent way of saying what the forces are. It would be the same as if we gave the magnitude of the force and the direction angle, and then you had to first find each component. It's just that now we don't have to do the work of finding each component because it's already sitting there in front of the unit vector. So normally we'd have to take our vector and the direction angle and resolve it into each component before we did the sum of the forces in each direction. But because in unit vector notation, the component's already sitting there, we can just go straight into our sum of the forces in each direction.